Any questions on what we covered last time? Okay, so what I'll do is for the next, maybe today and maybe next class, is still review of some of the material that we're going to need for the rest of it. You know, the communications courses, there's always a lot of math in there. And I know you've seen all of it, but you know, some of you have seen it a long time, or some of you have not understood why you need it at the time. So what I'm going to do is just quickly go through some basic concepts in probability. First, talking about probability as it comes to, as it's relevant to the random variables, and then what is more relevant for this course, I need to spend a little bit of time talking about random processes, because it turns out, as you already know, all of our signals that we care about are random processes. Right? So let's first talk about random variables. And when you talk about random variables, you have to talk about two functions that describe random variables. One is a probability distribution function or cumulative distribution function, and the other one is probability density function. So let's just go quickly through them. So I guess random variables. And then review. So the first thing that I'm going to talk about is probability distribution function. Distribution function. Or a more common name for this one is cumulative distribution function. Distribution function. CDF. So consider x as a continuous random variable. Which means it's a variable that takes values from some continuous data set in a random fashion. Then the CDF of this variable is defined like this. CDF of this random variable x evaluated at the point x0 is probability that this random variable x is going to be smaller than this value x0. So the definition is quite simple. You just have to think about it a little bit. If I have a function of a single argument, single input, single output argument, I give it a number, and what it comes out is another number. This function travels together with this random variable. So random variable is described by this function. And what the output is the probability of this random variable taking a value that is smaller than the input. Let me give you a more concrete example. Let's say this random variable here is height of a person, right? How tall somebody is. So that's a random variable. If you take population of people and you can measure height of each one of us, there will be a number. And that number is going to be a random value within a certain interval. Then the CDF would be, if I say, what's the probability of, if I feed, let's say, 6 feet to this function, it will give me percentage of the people or probability that a person is going to be shorter than 6 feet, right? So it's a very clear intuitively what this function, what does this function do? How do these functions look like? The typical CDF looks somewhat like this. This is the input x, and this is CDF of x. And then they look somewhat like this, right? They saturate at 1, and they're always positive. The value at any given input, which is x0, is this value here, CDF of x0. And CDF of x0 represents the probability of a random variable being smaller than x0. That's a graph of this kind of function. What are some of the properties of the CDF? first one, I already mentioned it. CDF of x is always between 0 and 1. Why is it always between 0 and 1? Because it's a probability. You know, it is telling me output is always a probability of a random variable being smaller than the input. So it has to be between 0 and 1 for every x. The second property is that CDF of plus infinity is equal to 1. This is a very loose notation on my part. What we should have here is the limit of CDF when x goes to infinity is going to be 1. But we all know what this means. If I do a physical interpretation of this, what does this mean? Probability that something or anything is smaller than plus infinity. What's the probability of that? 1. So it's a sure event, right? So that's what this means. That's why this one is never above 1, because in infinity it reaches 1. Probability of anything being smaller than infinity is a sure event. Likewise, CDF of minus infinity is equal to 0. Nothing is smaller than minus infinity. So probability of something being smaller than minus infinity is 0. The probability of such an event. The fourth property, probability that A is smaller than X, smaller than, let me make sure I get this, smaller equal than B, is CDF of B minus CDF of A. Probability that something is in interval between A and B is probability that is smaller than B minus the probability that it's smaller than A. Right? So this is probability that it is between A and B. Right? It is smaller than A, but yet larger than B. So it's minus probability that it's smaller than B. And then fifth property here, let me use this portion of the board. Fifth property is probability that X is greater than some value A is 1 minus probability that X is smaller than A, which is essentially 1 minus CDF of A. All of these are intuitive properties, but nevertheless, let's put them on the board to understand better what this function does and how does it behave. So let me look at an example, simple example here. Consider a function CDF of x given as 1 minus e to the minus 2x for x greater than 0 and 0 otherwise for x smaller than 0. How does this function look like? This is x, this is CDF of x. So it's 0 up to 0, and then it kind of moves like this until it reaches 1. Right? So it's not quite like this, but it's not that different either. Right? It kind of has this general shape. So what we are asked here is determine probability of x smaller than 3 and probability of x between 1 and 3. Right, so that's the two things. So let's look at the first one. Probability of x smaller than 3 is going to be CDF of 3. Right? That's essentially what CDF does. It gives you probability of being smaller than a given number. So if I plug in 3 here, this becomes 1 minus e to the minus 3 minus 2 times 3, right? 2 times 3, and this is 0.9975. So almost 99.6% of the time, or 6% of 99.6 or 99.8% of the time, this random variable is going to take the value that is smaller than 3. Right? So this is important for us, because if we design a system and we're dealing with random variables, we want to that's the only way how we can gauge how good our system is. If I design a system to be able to handle this random variable, and I make the range up to 3, that means 99.8% of the time I'm going to be okay, and I need to handle this small percentage of time where the random variable might be above the value of 3. Now, the second one is probability of x between 1 and 3, which is CDF of 3 minus CDF of 1, and this is 1 minus e to the minus 2 times 3, everything 1 minus e to the minus 2 times 1, and when I did the calculation, this is 0.1329. So 13% of the time, this random variable, or 30% of the outcomes of this random variable will be within this interval between 1 and 3. Any questions here?
Is that the same CDF or PDF like in the RF propagation?
Yeah, it's the same in every course. Right. CDF is this is kind of math thing, right? But it's used in every different course, right? And I kind of review it here because we all reach this point coming from different backgrounds. So I do this in a course, and then from now on, everybody knows what it is.
Is there one
Huh?
exponential minus 2 times 3? Is there one after that?
Print.
Where? Here? No, this is closed parenthesis here.
Oh, okay, there's 2 parentheses.
All right, so now let's take a look at the other function. It's probability density function. This is PDF. What is PDF? The simplest way to define PDF of x is derivative with respect to x of CDF of x. Right? So just formally, that's what it is. Now, how do these functions look like? Well, they have various shapes, but you expect to see something that might look somewhat like this. Now, in the case of a CDF, we attach the physical meaning to a particular value of the function. The value of the function had a physical meaning. The value of the function was a probability. In the case of the PDF, what we're going to look more, what we're going to consider more frequently is the area under the curve. We're going to attach physical meaning to the area under the curve. That's going to be the meaningful quantity here. And before I explain what it is, let's just review some properties of this of PDF. First one is PDF of x is always greater or equal to 0. Why is that the case? Because this is a derivative of a function that's monotonically increasing, right? Or at least non-decreasing function, right? CDF is always non-decreasing function. Why? Because probability, be careful, probability of being smaller than a smaller number is always going to be smaller than probability of being smaller than a larger number, right? So this function always has to grow, right? And something that always grows has a positive derivative, right? So the PDF is always positive. The second thing is integral from minus infinity to plus infinity, PDF of x dx. The area, total area under the curve has to be equal to 1, right? This is called normalization problem. Right now, let me get to the next property, and then we'll come back to this one and explain why this has to be the case. The third property is integral from minus actually, the third property is inverse of this, where we say CDF of A is equal integral from minus infinity to A of PDF of x dx, right? So this is an inverse statement of this one. When I say PDF is the derivative of the CDF, this is saying CDF is a primitive function for PDF, right? Undetermined integral of PDF, right? To get the CDF, you would integrate PDF from minus infinity to a particular point. Now, if you see, if you look at this property, and then you look at this one here, then how can you interpret this integral here? Integral from minus infinity to plus infinity is going to be CDF of plus infinity. What is that? 1, right? So, so that's the reason for this normalization property. And then last property that I'm going to kind of use this part of the board is that probability of A between X between B is going to be equal integral from A to B of PDF of X dx. So probability of a random variable occupying a given interval is going to be area under the curve or under the PDF curve over that particular interval. So unlike, as I said, in the case of CDF, where we attach physical meaning to the value of the function, here the physical meaning is attached to the area under the curve. And area under the curve between boundaries A and B represents the probability of a random variable falling within this particular interval from A to B, right? So that's a very important property that we're going to be using all the time. So let me just give, or let me continue now. Which one of these we're going to use? We're going to use both of them, and I expect you to be very fluent with both of them. However, more popular in its use is the probability density function. And you may wonder why, because this one is easier, right? The function itself is giving a physical interpretation. The reason why we use PDF is because what we're going to introduce now, and it's called expectation, right? Calculating of the expected value. So let me define what I mean by that and look at some common expected values and how you calculate those. This whiteboard has seen better days. It's not easy to erase. All right. So expectation, mean, and moments. And let me just say moments, because we'll see the mean is the same, similar thing. So here, so far we looked at only a random variable, x. Now I'm going to look at the function of a random variable. What's a function of the random variable? It's a function that the input argument, you give it a random variable, and it produces some value at the output, right? And most of the time, you know, you feed it an input as a random variable, you get another random variable at the output, right? So consider a function f of x, where x is a random variable. Then, expected value of f of x, which we kind of write like this. This E stands for expected value of f of x, is defined as an integral when x goes from minus infinity to plus infinity, f of x times PDF of x dx. So this is yet another function now, right? That you feed it a function of a random variable and it spits out another value, right? So it's very simple. I have a function. This argument is x. If I say expected value of f of x, this means nothing but this particular integral. And at that point, you just evaluate what that integral is, right? Because nothing here is, no, this is a function, this is yet another function. And if you can do it analytically, you do it. If you cannot, then you program it and do it numerically and move on. So let's look at some f of x's which are of a special interest to us. I mean, this gives you the solution in a general case for any kind of f of x. But there are some cases where f of x is of a special function and it holds quite a bit of interest to us. First case is f of x is equal to x. All right, this is a trivial, function, and you give it a number, it gives you the same number. Right? Now, expected value of x is going to be integral when x goes from minus infinity to plus infinity, x times PDF of x dx. Right? This is what we call mean value. Of random variable x, right? Sometimes we use the notation mu to designate, or expected value of x. This is what we call measure of center tendency for a random variable. It's its average value, its mean value, its expected value. All of these are used. How do you calculate expected value of a random variable for which you have a PDF? This is the way. How do you calculate expected value of a random variable for which you have CDF? You take the derivative of CDF, get the PDF, and then you use the same expression here. Let's say number 2, f of x is equal to x squared. So here, the expected value of x squared, just the same thing. X goes from minus infinity to plus infinity, x squared, PDF of x dx. This is what we call second moment. Okay? Second moment. Why is it a second moment? Because there's 2 over here. In general, if f of x is equal to x to the n, then expected value of x to the n is referred to, or actually, let me just write it. X goes from minus infinity to plus infinity, x to the n, PDF of x dx. This is what we refer to as nth moment. Okay? So how do I calculate x moment of a random variable? I have x of n, PDF of x dx. I claim that integral, and I get it down. Another special case for f of x, if when f of x is equal to x minus mu to the n. Expected value of x minus mu to the n, which is integral when x goes from minus infinity to plus infinity, x minus mu to the n, PDF of x dx, is called nth central moment. What is the central moment? It's a moment about the mean, right? Do you see, for example, it is straightforward to see if the random variable has a 0 mean, its nth moment and its central moment are the same, right? You see that? Right. So this is the nth central moment. There are a couple of moments that are, there's a special significance for us when n is equal to 2. Then expected value of x minus mu squared, which is your second central moment, is referred to as what? Variance. right? And then the square root of, how do I have it? Usually the symbol is sigma squared. And then this sigma, which is the square root of the expected value of x minus mu squared, is called how?
Standard deviation.
Standard deviation. Right? While the mean is the measure of a central tendency of the random variable, both variance and standard deviation are used as the prime indicators of the dispersion of a random variable. So it's common to say something is, let's say, 3 on average with standard deviation plus minus 1, right? Which tells you what is the central tendency, what's the mu value, and then this standard deviation tells you, well, how far can you be about that central tendency. And if a random variable is, let's say, 3 plus minus 0.1, you know it's practically 3. And if something is 3 plus minus 5, then who knows what it is. It's in between, 3 minus 15 and 3 plus 15. Right? So it's occupying taking pretty much any kind of value in the large integral. Any questions here? All right, so let me illustrate this through a couple of examples. Consider a random variable that has a PDF of x equal to 2e to the minus 2x, or x greater than 0 and 0 otherwise. Right? So that's a PDF of this random variable, and the question is find the mean and standard deviation. So find mu and c for this random variable. So how do I find mu? Mu is expected value of x, which I calculate as integral x goes from minus infinity to plus infinity, x times PDF of x dx. Right? Simple as that. Just take whatever is f of x, put it in here, and then attach this PDF of x dx. Now, in this particular case, this becomes an integral when x goes from 0 to plus infinity, x times 2e to the minus 2x dx. Why did I start from 0? Because PDF of x is equal to 0 whenever x is smaller than 0, right, according to this. So therefore, there's no need to integrate before 0. It's 0 anyway. So this integral I'm going to rewrite slightly. I'm going to say this is x goes from 0 to plus infinity, 2x e to the minus 2x d 2x, and then put 1/2 outside, right? Because I added 2x here. What's the value of this integral? Of the integral alone?
That's a 1.
1, right? So the whole thing is 1/2. One of the integrals that you guys should know, and I'm sure whoever, pretty much whichever course you took from me, you saw this integral, because it appears all the time. And this is this guy, integral when t goes from minus 0 to plus infinity, t to the n, e to the minus t dt. What's the value of this integral?
N factorial.
N factorial, right? That appears all the time. So if you look at this, where if I put t equal to 2x, then this here is what? 1 factorial, which 1 factorial is 1, so it's 1/2. This one keep handy because it's going to be appearing all the time. It's going to help us a lot in integrating. So how do I do standard deviation? Standard deviation, there's this square root here, right, which we're going to deal at the very end with. So the way how you calculate standard deviation, you calculate the variance first, and then you take the square root of variance. So variance let me actually do it slightly different in the notes. Variance is equal to expected value of x minus mu squared. Right, this is the definition of the variance. I could proceed as I did here in the notes and plug that in directly and do it, but let me give you another approach because it's more useful. So instead of substituting this directly, let me say something like this. This is expected value of x squared minus 2x mu plus expected value of plus mu squared, right? Expected value of this, okay? Now I can, expectation is a linear operator, means that expected value of the sum of terms is the sum of the expected values. That comes from the fact that the expected value is nothing but the integral. An integral is a linear operator itself. So I can write this as an expected value of x squared minus 2 times mu. Mu is a constant, right? It's a mean value of this random variable, so it's 2 times mu, expected value of mu, and then plus mu squared.
Expect
Expected value of x.
x.
Okay? Now, what's the expected value of x?
Mu.
Mu. So I have minus 2 mu squared plus mu squared, right? So this is expected value of x squared minus the expected value of x, which is mu quantity squared, right? Did I introduce any assumption of what the PDF of x is? No. So this is always true. Variance can be seen as a difference between second moment and the first moment squared, regardless of the PDF. You know, I stress this maybe unnecessarily, but when I was sitting where you are, you know, that was always, I remember this property. Is it always true? You know, does it depend on the PDF? Is it only for normal? You know, this is always in my head. And then the answer is no. This is a general property that holds for any random variable. You can determine its variance as a difference between second moment minus the first moment squared. Right? So why I do that? Because since we already have the first moment, I don't need to calculate this part here. Let me just calculate the second moment and then take the difference. So what is the second moment of this variable?
Excuse me, Professor.
Mhm.
I have a question.
Go ahead.
So the second moment actually is a kind of like derivation from the first moment?
Is what?
Derivation.
No. The second, this is the definition of the moment, right?
Right.
X to the n. So for n equal 1, you get the first moment. For n equal 2, you get the second. For n equal 3, you get the third, fourth, and so on, right? So there are, you know, just an easy definition here.
The second one is actually a DC component. Is that the one? DC
No, the
component?
first moment can be understood as a DC component.
Oh, the first moment.
Second moment can be understood, the first moment is the DC component. The second moment can be understood as a total power.
Oh.
And then if you look at what this means, and then a variance can be understood as an AC power. So what this says is the AC power is the same as the total power minus the DC power, because the mean value squared is your DC power.
Yes.
Or if you bring this to the other side, total power is AC power plus DC power, right? That's the one of the physical interpretations of this. So let me calculate the second moment of this random variable. So in this case, expected value of x squared is going to be integral when x goes from 0 to plus infinity. Then you put x squared, or let me just go from minus infinity to plus infinity, PDF of x dx, just a general expression for the second moment. in this case, this is an integral when x goes from 0 to plus infinity. Then I have x squared. Then I have 2x e to the minus 2x, and then dx. Right? So that's just substituting the PDF in there. And then let's play with this integral a little bit. So this is x goes from 0 to plus infinity. I'm going to have 2x cubed e to the minus 2x d2x. And then let's see here. I had one 2x, so this is here.
Is it? It's 2, not 2.
Say again? Oh,
2.
2. Okay, so then 2x squared. All right? So let's see here. I have 2 that went in here, so I have to divide by 4 to make everything balance, right? Because I've added 4 here. Okay? Now, what's the value of this integral? Then say 2 factorial, which is 2. So this whole thing is 1/2. Right? So if I now go and calculate my variance, variance is going to be expected value of x squared minus expected value of x squared, which in this case expected value of x squared is 1/2 minus expected value of x is 1/2 squared is 1/4. So the whole thing is 1/4, and therefore sigma is 1/2. So this is a random variable that has a somewhat special property that its mean and standard deviation are the same. What kind of distribution has this property?
Exponential.
Exponential distribution. There you go. Right. So if you get some measured data, and first thing you always do, you calculate its mean value and standard deviation. And if 3 things happen, first all the measurements are positive, and the mean and standard deviation are the same, the likelihood is that the variable is exponentially distributed, or can be successfully modeled as exponentially distributed anyway. Turns out a lot of times that happens, right? That's what I'm telling you.
I have a question again.
Go ahead.
Why we need to understand, calculate, we have a lot of data, but where does it come from? The data from the DSP, something like that, or communication, something?
Okay, let me refresh your memory. Let's say I take a lot of measurement of the signal power.
RSL.
In this it's RSL, but RSL is in dBm. Let's put it back into the power domain and express it in milliwatts. And then I take those measurements and I take the mean and standard deviation, and they happen to be the same.
Oh, okay.
What kind of environment I'm talking about? Starts with R. I have a
Random variable?
no. What kind of fading environment I'm talking about?
Rayleigh.
Rayleigh fading environment, right? In Rayleigh fading environment, my power is distributed how? Exponentially, right? Exponentially. That's one, why do we need to know? That's one application there, right? In the other course that we're taking, like personal communication systems, what you would discover is that something called co-holding time is exponentially distributed. If you were, it's fascinating because, you think this is just pure math, right? But it has a very, almost, I don't even know how to call it, voodoo kind of relationships to stuff around us, right? There's a lot of things that are where this distribution comes up, where, a lot of natural phenomena are explained using this distribution here. Like if you look at humans, us as a sources of information, and you look at our ability our willingness to communicate, it's always exponentially distributed. What do I mean by that? If you look at duration of our phone calls, it's exponentially distributed, right? We don't talk for a very long time. We get impatient, so it kind of falls off right away, right? They're mostly short calls, and then probability of us talking longer is ever so smaller, right? When we text, the same thing. When we type emails, the same thing. So whenever we are principal sources of information, this distribution pops up. How long do we want to wait? Exponentially distributed. We are very impatient, right? And that's completely different than computers. Computers are happy, you know, you start downloading movie, and it will download for, 3 months if nothing extraordinary happens, right? We don't do that, right? So wherever there's something attached to us, this distribution comes up, right? It's very interesting to me, at least,
Wherever you have exponential, then it comes with.
Yeah, and that, in my opinion, this is what links us to this world, because this whole world somehow is exponential, right? Whenever you're describing something and it's natural phenomenon, always look, where is exponential? Somewhere here, right? If you look at, a lot of times, like even unrelated things, like from skin depth of RF penetration into different materials, to the decay of the radioactive components, to all sorts of things, right? Everything is exponential. And that's one that will occur all the time. The other one that occurs all the time is something that we call normal distribution, normal PDF. Or another word is Gaussian. This one is going to be very important to us because we'll be communicating in AWGN, a channel that is corrupted with the noise that exhibits this kind of properties. We say that the random variable has a Gaussian distribution, and we indicate this like this, that this is a random variable that follows Gaussian distribution with two parameters, mu and sigma. The PDF of the Gaussian distribution looks like this: 1 over square root of 2 pi sigma squared, 2 pi sigma, sorry, e to the minus x minus mu quantity squared over 2 sigma squared for every x. Okay? So that's a normal distribution. It has these two parameters, mu and sigma, that have distinct interpretation. Expected value of x is going to be mu, and expected value of x minus mu squared is going to be sigma squared. Right? So mu is the mean value or expected value of x, and then sigma is the standard deviation of that random variable. These distributions look like this. They are centered around mu, and they look like bell curves. And the opening of this curve is proportional to sigma, right? So for larger sigma, the curve is more open, which means that there is a larger dispersion of this random variable. It can be anywhere. For small sigma, these become more and more narrow, so that means the random variable is just in this smaller, ever smaller interval that is centered around the mu. The importance of this distribution is so big. It turns out, and there is something called central limit theorem that tells us that whenever we have a random variable that is a result of many underlying phenomena, right, then it tends to be exponentially, normally distributed. Earlier today I talked about the height of the person, right? If you look at what that depends on, there are many things, right? Your parents, genetics, race, whether you're athletic or not, how much do you eat, and so on. So there are all of these unrelated things. And if you take like a population and do actual measurements, they will be distributed like this. Right? And we actually did that in high school, and it's one of the ways how you get an intuitive feel of this. So whenever you have a random variable that is a result of many processes that are unrelated, then some of these processes tends to be following normal distribution.
Is that square root over the whole?
No, that's why I erased the square, right? So the square root stops here. So it's square 1 over 2 pi, and then sigma is outside. Good question, because that's always a source of mistakes. All right, so that's my really quick review of the random variables. Essentially what you take out of this is PDF, CDF definitions and how to calculate expectation values and what do moments mean and what do central moments mean and how do you calculate mean and standard deviation. Those are the things that you need to be really fluent in. There are other things that we're going to use, but then I'll introduce them as we need them. I'm going to use this universally all the time, and that's why I extracted it as a separate review. Let's talk about random processes. So most of the signals that we care about are random processes. You know, there's very little point of transmitting deterministic signals, right? If the transmitter knows what the signal is, and you know it's not a random, it's like a square wave pulse. All I need to say to receiver, hey, it's a square wave pulse, and you generate it over there. I don't need to waste bandwidth or energy to transmit it, right? So all of our signals, music, voice, video, whatever it may be, data, are random signals. The value of the whole system is to send to the other end something that the other end doesn't know about, right? So that's where the whole system is important. So we're in this really, how should I say, funny situation that we're designing a system, communication systems, for the signals for which we know what they're going to be, right? We're designing for random signals. And that seems like a really difficult task, but it's not that difficult, because what we need to do is we need to describe the signals in a statistical sense. And we already kind of started that by describing random variables, which can be seen as one dimension of a signal. The second description that we need to give to the signal is its behavior in time. So the way how you, I mean, there are precise definitions, but I'm deliberately staying away from them because I want you to get a feel. Random processes, you can think of them as the random variables through time, right? You have this magnitude that's a random variable, and then you have this random variable traveling through time. So there are two descriptors that we need to attach to a random process. Its behavior in the magnitude domain, where every random process is going to behave like a random variable, and then its behavior through time, where we're going to use either autocorrelation or power spectral density or either time or a frequency descriptor to describe it. But when I talk about random variable, all I need to give you is a single function, either PDF or CDF. When I talk about random process, I need to give you two things. One is going to be PDF and CDF that will describe the random process along the y-axis in the amplitude domain. And the other one will be some form of descriptor that will explain how does this random variable travel through time. And I can give you either time domain descriptor, which would be in the form of autocorrelation function, or frequency domain descriptor, which would be in the form of the power spectral density. So that's abstract. Let's just go and go step by step here. All right, so when we talk about random processes, we start by something that's called sample space. This is an abstraction. You can think of this as a set, which can be, it's usually infinite, where every element of this set is a realization of a random process. So this is, let's say this is S1, S2, S3. And this point in the sample space actually translates into a realization of the random process, which might look however it looks like. This is S1 of t. This is maybe S2 of t. And so on, right? So this is this guy, and so on. Now, let me give you an example. What is a sample space? When we refer to as sample space, we say something like speech signal. What is a speech signal? That's a set that contains everything that anyone has ever said, plus anything that anyone would ever say, right? So it's a pretty large set. As a matter of fact, it's infinite, right? And it contains all possible realization of the speech signal. When I say what are the elements here, this is tonight's lecture, right? One possible realization of the speech signal. This is 6 o'clock news. This is, all this is, Barack Obama's speech or whatever, right? So these are all possible realizations of the speech signal, right? Now, where do these descriptions come into place? First, if I freeze time, let's say I look at what happens at this time t equal Tm. I don't know where m is coming from. Then you can see that at any given time, if I line up all of these elements of the space, they're going to all be represented with a single value, right? What is this value going to be? It's going to be a random variable. It's going to be changing from sample to sample. So I'm going to have infinitely many realizations here, and each one of them is going to be a value, therefore it's going to be a random variable. So what I can do is, at any given time, I can attach probability density function to this random process. At any given time, in an amplitude domain, there is a PDF that describes this process, right? So if you look at this time here, you can probably say at this time, there's going to be some PDF of this S at a given time Tn, right? That will tell me how the values of this signal are being distributed. So if I look at different time, let's say this time here, so this is time Tn, there may be a different distribution, right? Let's say distribution that looks like this. So this is PDF of this signal S at the time Tn. Right, so this is some S, right? So in general case, the distribution of the signal may change over time. This kind of signals we call non-stationary, right? Because non-stationary in the amplitude domain, because their properties in the amplitude domain change over time, okay? Let me ask you this, what's your intuition? If this is a speech signal, right? What's your intuitions? Do these properties change over time?
It's random. Because it's random, it will change over time. You
But
don't have any
the
like-
values will change, but the distribution?
No.
No, intuitively, right? If this is everything that everybody ever said, if I look at any particular time, why is it different than any other time, right? It shouldn't be, right? So there are a lot of signals for which, even though individual realization change all the time, and the overall statistical behavior of the signal does not change. So if I have PDF that describes this signal in the amplitude domain, constant over time, I'm talking about stationary signals in the amplitude domain, right? And this is very important class for us. Why? Because if I work with the stationary signal and I design my system to handle this particular PDF, then I'm sure that over time it will handle all possible realizations, right? Because the signal will not change statistically, right? And if we design our phone to handle speech signal, then it will handle it today and tomorrow and 3 months from today, right? So stationary signals means that the property of the signal does not change over time. And here I talk in particularly about stationarity in the amplitude domain. What that means is that the signal PDF does not change over time, okay? That's the very strict definition of the stationarity. So if PDF of S does not change over time, signal is strictly stationary, strictly in the amplitude domain. Okay? That's the definition of the strict stationarity. There's a milder definition, more mild definition of stationarity that is a lot of times just as, I guess, all that it is required for a lot of algorithms. And this is definition of wide sense stationarity. And you know, in other courses that even I teach and other professors teach, we always say, there's always famous introduction saying, assume that the signal is wide sense stationary. So what does that mean? When we say the signal is wide sense stationary, we are requiring that only first two moments stay same over time, right? So if mean and variance of the signal stay constant over time, the signal is wide sense stationary. Wide sense stationary. Well, again, what is the difference between the two? This is a much more strict condition. You are requiring that the entire PDF stays the same. What that means is all moments are the same. First moment, second, third, 105th moment is the same all the time. Because the entire PDF does not change. But the PDF might change, but as long as the mean value and the power does not change, then the signal is considered as a wide sense stationary. And you will see in signal processing, especially like adaptive signal processing, this is all that is required for most of our algorithms because we are focusing on signal to noise ratio, kind of power over power, right? So, and the powers are captured in the first two moments, right? AC and DC power. So wide sense stationary signals in the amplitude domain, so wide sense stationary in the amplitude domain. For wide sense stationary signals, we know that the first two moments don't change over time.
Excuse me, Professor.
Go ahead.
I have a question.
Uh-huh.
Would you give a simple explanation, practical idea of the wide sense stationary and then like the amplitude domain stationary?
Well, let me give you first example of non-stationary signal. Okay. Let's take a look at satellite communication, right? And you have antenna pointing to the satellite. The noise of the antenna at the antenna output depends on the background radiation that it encounters, right? What is coming through the antenna. Now, we have what changes over the course of 24 hours? Day and night, right?
Right.
So if you have the same antenna pointing to the sky, and you look at the noise coming out of the antenna, here's what you're going to have. You're going to have a signal that looks like this. Overnight, it's small power, then there is a morning, then here is where the sun goes through the main beam of the antenna and then it falls down. That's a non-stationary signal, right? Because its properties change over time, right? In times when you are not pointing towards background radiation, and there is nothing, and then there's sun going through the main beam, and then it falls off. So here, you have a noise signal that has a non-stationary behavior. Right? If you have a
White station?
hmm?
White station?
If you have a tube amplifier, right, and it's in an air-conditioned room that is always on the same temperature, the noise is going to be the same, right, all the way through. So that's an example of a stationary signal. If you are listening to radio broadcast, because it's such a low frequency, the noise stays relatively the same.
But
So
it
that's a
depends on
stationary.
the system. I mean,
Huh?
it depends on your environment, circumstances.
Correct.
You
Yeah,
cannot
depends
say
on
that.
your environment. Even in this case, what we realize is this. It is non-stationary if I look at it over a period of 24 hours. But if my communication session is this long, then over duration of the communication session, I'm still dealing with the stationary process, right? Right? So here's the bottom line. We like it to be stationary, right? And we try to find out a way to model it as stationary, because if it's non-stationary, then the math becomes much more complicated, right? So we find out ways, or we look for ways how to devise something that, how to model something as a stationary process. And a lot of times, luckily for us, we can do that, right? When I talk about communication over, let's say, cellular link or communication over a terrestrial link, even though every time I pick up the phone and I connect, I may actually have a different noise to deal with. But over duration of this conversation, the properties of the noise may stay the same. So I can imagine that what I've observed is just a small portion of a large signal that has the same properties. In other words, I can imagine that this extends all the way to infinity, and I wouldn't be wrong for this particular void, for this particular session.
You just
So
put the samples on that and then
Yeah.
put decide that.
yeah, so that's the difference. So stationary means the signal statistically stays the same, right? And then we follow from there, and we have tools to deal with it. Okay. Now let me introduce another property here, which is also fine property that let's see if we can understand this one. And this is the property of ergodicity. So ergodic process. Okay. Now, here's how did we define a moment associated with a given random process? We did this. We froze the time, and we look at expected value across all these possible realizations. In other words, we said, well, at any given time, there's a PDF, and I can define, for example, mean as expected value of these points that are at a given time. Right? This type of averaging is called ensemble averaging. Right? You're freezing the time and looking the moment across all of these possible realizations. What is the bad about this? What is kind of tough about this approach? These dots, dot, dot here, because there's infinitely many of these, right? And usually, a lot of times, you don't have many. You just have one, right, that you're dealing with. So what I need to understand is, can I work with one and draw conclusion about all of them? In other words, if I take a very long speech signal and I design my system to work for that signal, would it work for all the other signals that I haven't considered, right? And for example, and if I take this long speech signal and I take its average, is this average that I obtained by averaging in a time domain going to be the same as the average across all of these different realizations of the speech signal, right? So that's the fundamental question. There are processes for which this is the case indeed. So let me first define what we call ensemble average. So if I have x of t is a random process, and I have a function f of x, f is some function, then I take expected value of f of x of t for some t equal to t0. And this is an integral when x goes from minus infinity to plus infinity, f of x times pdf of x at that time t0 dx. Okay, it's a little bit clumsy in terms of notation, but it's very clear what I'm trying to do. I'm defining ensemble averaging as this. I freeze time, so t is equal to t0. And then at that given time, I have the distribution of the magnitudes for this particular random process, right? I'm looking across all possible realization. Every realization will take a single value. Therefore, I'm going to have a distribution of these values that I describe with this PDF. So expected value of the function is what we defined earlier, is expectation of this using this PDF, right? Normal expectation. So this is what we call ensemble averaging. I'm obtaining the expected value of the function by at any given time. If the signal is stationary, what happens here? If the signal is stationary, then it doesn't matter what the t0 is. I get the same result regardless of the t0, right? Because I can freeze time at any point. I'm going to get the same PDF, and any kind of averaging, I'm going to get the same value, right? So that's ensemble averaging. Now, the different approach is what we call time averaging. Here, I don't have many signals. I have f of x of t. So I have the function of this single signal, x of t. And let's say it looks like this. Then I can define the average of f of x, now in time domain, as a limit when t goes to infinity, 1 over t, integral over t, f of x dx, or f of x, f of x of t. And then here, f of x of t dt. So I'm averaging now by taking the average over time. Remember this integral, 1 over t, integral over t, something dt, that's time domain average, right? This is how we determine the power of the signal, you know, in other courses. So let's test this a little bit. Let's look at these guys and assume, for the sake of our mind experiment, assume that this is noise, thermal noise on some resistors, right? What's the average value? If I have 100 different resistors, 100 of the same value, and I look at the noise on each one of them because the electrons move through these resistors, what's the average value? 0, right? So if I do ensemble averaging, you know, by putting these 100 resistors here, plotting all of their noise values, stopping the time at any given time value, and then looking across all of these possible realizations, intuitively I'm going to get 0, right? Because there's no reason why the electrons would prefer going this way versus this way. In some of the instances they're going this way, and the others they're going this way. On average they're going to be, you know, they're not going to go anywhere, just going to move around. So that's a ensemble average. But what is the explanation of this? I take one of these resistors and I observe it over a long time, and I say, well, what is the average current flowing through this resistor? And what's the intuitive answer to that? It's 0 again, right? Because whatever went this way, you know, now the next second is going to go this way, and then they're going to be just going back and forth, right? So there are a large class of processes for which this kind of behavior holds true. What is the best intuitive feel for this? Imagine me taking this one resistor, right? and observing it for days. So get a very long signal here. And then take this long signal and take scissors, right? And cut it into small pieces. And then I stack those pieces like this. Can I tell the difference between this and then ensemble? No. So if I look at my speech signal, theoretically, if you let me speak for an infinitely long time, I'm going to say everything that everybody has ever said, right? Because I'm going to run out of, unless I start being periodic at some point. But I'm going to essentially recite, you know, Romeo and Julia and move to other stuff, right? So say everything that everybody said, right? So that's an example of an ergodic signal. If you let one signal go for a very long time, it will actually go through all the phases of all the elements of this sample space. Go ahead.
Yeah, you talked about ensemble average of the resistance, and now somehow you jump from the speech. I think from the speech it depends on the frequency. But if you come with the time average of the resistance, it depends on your.
These are just two examples I gave. I mean, I finished with resistors and then went to speech. Right?
Oh.
So as far as resistors, right? If I observe the voltage on a single resistor for a long time, and let's say for a very long time, and then I cut this signal into pieces, and I arrange it like this, it would look as if I have monitored many different resistors for a relatively short time, right? You wouldn't be able to tell the difference.
Right.
So what that means is that for these kind of signals, ergodic signals or ergodic processes, observation of one signal or one process for a long time would give you the same information as observing many processes, right? Which is a beautiful thing that we have, because I can now design my system to handle a single noise, and have a confidence that it will be able to handle any noise, because this one here is indistinguishable from any other ones. Okay? Let me give you an example. Let me first give you homework assignments, because the weekend is coming, and you don't want to waste the weekend, right? So, and then I'll try to give you a counter example so that you understand a little bit better. So let's do 4/8, 4/9, 4/10, 4/13, and 4/26. They're all kind of exercising PDF, CDF, and all of this stuff. Let's look at an example of process that is also a random process, but it's not ergodic, because to me it was this was an unclear concept until you get a counter example, and then you get it. Okay? So let's take a bunch of students in electronics lab, right? Right. And they all there's a fire alarm and they all leave, right? And they leave their power supplies and whatever value the power supply was when they were doing experiment. So let me plot those. This is a student number 1, and he didn't even turn it on. So this is 0. So this is voltage 1. Here's the student number 2. He left it at this value. Here's the student number 3. He left it at this value. Right? And there are many students. Intuitively, if they were all setting these power supplies and in a random fashion, what is the expected value across the average, across the sample? 0. So if I do ensemble averaging here, the expected value is 0. But let me pick one of them, let's say V2, and I do time domain average. What is the value? No, good. It's 5. Yeah, so here, if I take one process, I'm going to get different time domain averages than what I get when I do across the ensemble. This is a non-ergodic process. It is random, right? At every instant of time, it is stationary too, because at every instant of time, if I look at the PDF, it's uniform between minus VCC and plus VCC, right? Random value in between there. But if I look at whether the time domain averaging and ensemble averaging will give me the same value? The answer is no, right? Because this, if I happen to pick this one, I would get 0. But if I happen to pick this one, it will be 5, it could be -5, and so on, right? So this is a non-ergodic process. When you compare that against the noise was different. Every one of these went through all possible values, so the time domain averaging and ensemble domain averaging are going to give us the same value. Now, we kind of luck out here too. In a lot of cases, and we're mostly concerned about noise in the system, thermal noise. All of our communication is going to be against some sort of noise and interference. It turns out that you can model this noise and a lot of times interference as ergodic processes as well. And since this is introductory course, I'm going to actually use this mostly, right? Mostly talk about time domain averaging, assuming that it's the same as the ensemble domain average. In a book, they talk about something called cycle stationarity and all that, and we're going to stay away from that.
What?
Because just to simplify, because you cannot cover everything, right? But just be aware, and I'll try to point out if something is not ergodic, then I'll point out, and there will be a couple of places in the course where I indicate it. But for the most part, we're going to treat our signals as being ergodic, so that I can take the time domain average and substitute that for the ensemble domain averaging where I need to do. Okay? All right. Thank you.